So we are on to chapter 10, which is chemical bonding 1, the Lewis model. Chapters 10 and 11 go very much hand in hand. In chapter 10, we're focused on looking at these molecules in 2D space. So we're going to start seeing how molecules are connected, how are compounds connected, what's actually put where. And in 2D space specifically, we're going to start thinking about things like electronegativity, how electrons are actually shared, where the electron density is, different concepts we've talked about, but pulling them all together. Chapter 11, we're going to start looking at these molecules in 3D space and start really examining the types of bonds that are occurring. So your chapter 10 focus, we're going to do a review of ionic, covalent, and metallic bonding. We're going to talk about Lewis dot symbols. We're going to talk about the spectrum of ionic and covalent bonding, lattice energy or Coulomb's law, covalent bonding. Within covalent bonding, we have pure covalent, nonpolar covalent, and polar covalent. Lewis structures, including your octet rule and exceptions, formal charge, and resonance. We're going to examine a series of organic molecules, electronegativity, and how that factors into polarity of overall molecules, and bond energy. So for Module 10A, you guys can go ahead and read through this on your own, but it covers what we're going to cover in this module. So as a little bit of a review, ionic and covalent bonding. There are 3 types of chemical bonding: ionic bonding, covalent bonding, and metallic bonding. We don't spend as much time talking about metallic bonding. We'll spend more time on that when we get to the solid state chemistry chapter, but we do have a brief definition of it. But let's talk about ionic bonding. Ionic bonding, again, involves the electrostatic attractions between oppositely charged particles. So here I've got a sodium atom. Here I've got in a sodium ion. So atom versus ion. What do I mean by those terms? Find a color that you guys can see. So atom versus ion. Here I've got a chlorine atom. Here I've got a chloride ion. Remember, when anions become it, when nonmetals form anions, an anion, we change the ending of that name to "ide" to represent that it is an ion. For cations, we just put the word ion on the end of that name. But sodium, a sodium atom, loses an electron. It gives an electron entirely to a chlorine atom, forming a sodium ion and a chloride ion. I now have 2 fully oppositely charged particles that are attracted to each other. That's an electrostatic attraction of that oppositely charged particle. So the electrons from my chloride are attracted to that positive nucleus here. That positive nucleus is attracted to these electrons here. Does it have its own electrons? Yes, it has its own electrons, but that's still how it's holding together. It's actually quite a strong bond to be able to put these things together. We have covalent bonding. Covalent bonding is when we're sharing electrons, and this is typically observed between nonmetals. I say typically because in Gen Chem we tell you it's not covalent bonding is non-metal bonding. That is true to a point. The truth is Gen Chem lies to you a lot. We oversimplify things a lot so that you guys can start to understand concepts, and then we build upon what you've learned. What we actually find is that there's this difference in electronegativity. We're going to discuss electronegativity at the end of the chapter. But this difference in electronegativity of the different atoms themselves that leads to how ionic or covalent a bond actually is. And so even if I have a metal and a non-metal, it may actually behave as a covalent bond just due to the difference in electronegativity. But traditionally, we say covalent bonding is between nonmetals. We are sharing electrons, and 2 electrons create 1 bond. The properties of elements and compounds are consequences of the types of bonding exhibited. So, ionic bonds, we see these ionic compounds. They have high melting points. They're hard compounds. They tend to, depending if they're soluble, they conduct electricity. Covalent compounds tend to have lower melting point, lower boiling points. They tend to not conduct very well. They are they're non-electrolytes. So whereas ionic compounds will be either strong or weak electrolytes, molecular compounds are covalent, and those will be non-electrolytes. Metallic bonding is when you have your metal cation sitting in a sea or ocean of electrons. This is typically observed between metal ions. So if you look here at the screen, we've got a bunch of little sodiums. The little yellow circles are sodiums, and underneath that little yellow negative signs are all of your electrons floating around, and here for zinc as well. So what we actually have is your metal cations, and then we have what we call a sea of electrons. The electrons are able to flow around freely. This is what allows metals to conduct electricity so well, conduct heat so well. The electrons are able to freely flow. Bonds form when they lower the potential energy of the atoms or ions. It's an exothermic process when bonds form. So bond formation, exothermic energy is released. That's the whole reason a bond is forming. A bond is not going to form if there's not a reason for it. The two driving forces in chemistry are energy and disorder. We talk about disorder in second semester. This semester we focus on energy. Again, it's not going to happen if there's not an energetically favorable reason for it to do so. Lewis dot symbols you may or may not remember from high school. Lewis dot symbols basically show us how many valence electrons an element has. So you can see here we've got a series of them listed for you already. We'll draw out the others in just a sec, but we see here our Lewis dot symbol. To figure out your Lewis dot symbol, you need to find your valence electrons. How many valence electrons does it have? The quick way to do it when you're looking at the periodic table is you've got groups 1 and 2. You've got your transition metals, which I'm going to truncate for space. And you've got your P block. 1, 2, 3, 4, 5, and 6. Ignore your transition metals. 3, 4, 5, 6, 7, and 8. These are what we call the old group numbers. This tells me how many valence electrons I have. So for example, sodium is in this column. Sodium has 1 valence electron. Calcium's in this column. Calcium has 2 valence electrons. Let's see, aluminum is here. It has 3, I don't remember which order these are all in. Carbon, nitrogen's in this column, oxygen, fluorine, neon. I don't know if those are all in the same row or not, but I know they're in the right columns at least. Aluminum has 3 valence electrons. Carbon has 4. Nitrogen has 5. Oxygen 6. Fluorine 7. Neon 8. If you're unsure how to do that, so that's just counting across and ignoring your transition metals. And we count across how many valence electrons we have. Otherwise, you can write your abbreviated configuration, and it shows you there as well. A few students have asked me about transition metals. How do you know how many valence electrons they have? Remember when you're in these transition metals, I think I'm trying to make 10 spots there. I'm not sure how many spots I just made. But remember, if I fill say I fill this first row of my transition metals. This is your 3D. This is 4s. This is an inner core electron. So for example, zinc, which is over here, zinc has an electron configuration 4s2 3d10. That means zinc only has 2 valence electrons because this is core. This is valence. Let me back up a little bit and let's actually do the ones we have written out on the slide though, as I get kind of carried away on other stuff. So lithium, 1 valence electron, it's group 1, I put 1 dot. Beryllium, 2 valence electrons, it's group 2, I put 2 dots. Boron, 3 valence electrons, 3 dots. Note that I am not putting the dots together. I am doing the equivalency of parallel before paired that we learned about in chapter 10 or chapter 9. Remember we talked about in a P block how we do parallel before we pair up electrons. We're doing the same thing here with the dots. We have 4 sides to an element. So let's just say letter A. Letter A isn't really an element, but we'll say it is for a sec. We got 1, 2, 3, 4 sides. We individually put those electrons in before we pair them up. And that's what we see happening on our examples over here. So if I was to write out the Lewis dot symbol for each of these elements, sodium 1 dot. It has 1 valence electron. Magnesium, 2 dots. I don't care if you write it like this, like this, like this, this, whatever. I don't care. That part doesn't matter. What matters is that you only have 2 dots and they're not written on the same side of the magnesium. Aluminum, 3 dots. Silicon, I'll write it out here for some space. 4 dots. Phosphorus, 1, 2, 3, 4. Now I have to pair up. 5. Sulfur, 1, 2, 3, 4, 5, and 6. Those should both be, I didn't draw those very well. Those should both be on the side. Chlorine, 1, 2, 3, 4, 5, 6, and 7. And argon, 1, 2, 3, 4, 5, 6, 7, and 8. Note there's 2 on each side for argon. 1, 2, 3, 4, 5, 6, and 7, 8. So we parallel them before we pair them up. Make sure you're doing that every time. Okay, ionic and covalent bonding, a continuum. Please note that if you are using the student notes, I don't know why, but somehow I put nonpolar here and polar here, and they're switched in the student notes, so please write them in the right spot. I didn't realize that until after I was teaching. And so in my current student notes, they're backwards. And I just want you to make sure you're writing them in the right spot. Ionic compounds, full transfer of electrons. Covalent is sharing of electrons. Nonpolar covalent is when the electronegativity difference between the 2 atoms is so small it's considered nonpolar. And we haven't learned electronegativity yet, but it is coming. So we say there's an equal sharing of electrons. There's the values we use to determine this. You can have pure covalent. Pure covalent is when you have something bonded to itself. So like H2, O2, F2, Cl2. That is pure covalent. Those atoms that are bonded to each other have identical electron configuration. We also have what we call nonpolar covalent, like carbon-hydrogen bonds. Carbon and hydrogen have a difference in electronegativity. Carbon is, I believe, 2.5, and hydrogen, I believe, is 2.1. You don't need the numbers memorized. You just need to know that they have a small enough difference that they are considered to be nonpolar. Even though there is a difference in electronegativity, which means there's a slight unequal sharing of electron density, we consider it to be nonpolar. Polar covalent is when we have 2 atoms that have a large enough difference in electronegativity that it's an unequal sharing of electron density. So in chapter 8, we talked about how electrons can behave as both particles and waves. In this sense, I need you to think about an electron as a wave. And in my mind, I actually picture a cloud. I think of it as an electron cloud. That's a term that was always used when I was learning chemistry, and so I actually picture it as a cloud. This cloud of electron density, this cloud that contains the electrons. Chlorine is a more electronegative element than hydrogen is. And so we can write this one of 2 ways. We can write this partial negative, partial positive, or you'll also see this written as an arrow with a line. This is a dipole. What this is telling me is that the electron density is being pulled towards the chlorine. It's an unequal sharing of the electrons. So even though there's technically 2 electrons in a bond here being shared, 1 electron from hydrogen, 1 electron from chlorine, chlorine is pulling the bulk of that electron density to itself. So it's unequally sharing those electrons and selfishly holding on to more of the electrons than just half of that bond. So I have the little cartoon here is supposed to help you guys remember this. Ionic bond, covalent bond, and polar covalent bond. An ionic bond. Hey, Eugene, would you like a cookie? Just full, give away the cookie. A covalent bond. Let's split a cookie 50-50. It's an equal sharing of electron density. Polar covalent bond, 7/8 for me, 1/8 for you. An unequal sharing. Okay, ionic bonding and lattice energy. What is this lattice energy that we talk about? I need you to consider a binary ionic compound. Binary means 2 atom, or in this case 2 ion because it's ionic, between a metal atom and a non-metal atom. There are 3 things that we need to consider in terms of energy. First, metals have low ionization energies. Remember, we talked about ionization energy in chapter 9. Ionization energy is the amount of energy required to remove an electron from an atom or ion in a gaseous state. Metals we have to pay the metal to give away that electron, yes. Sodium isn't just going to give away its electron for free. It requires payment, but it's pretty low payment comparably. It doesn't cost me a lot to remove that electron from sodium. Nonmetals have high electron affinities. Electron affinity, so ionization energy, remove electrons. Electron affinity, add electrons. Electron affinity is the energy required or paid by an atom to add an electron to an atom in a gaseous state. So nonmetals, electron affinity, how much do they like an electron? Nonmetals really like electrons. Nonmetals like electrons so much they're willing to pay you for them. How much are they willing to pay? Well, a lot, because they have high electron affinities. They're willing to pay a lot of energy for it. And energy is released when gaseous ions form a solid crystal. So if I have Na gas, or Na plus gas, sodium ion, plus a chloride ion in the gas phase, and it forms NaCl solid. This is exothermic. It releases energy. So how does this factor into lattice energy? Lattice energy is the energy required to completely separate 1 mole of a solid ionic crystal into the ions far removed from each other. So I just told you, putting this together, what if instead I took NaCl and split it apart into Na plus gas plus Cl minus gas? How much energy does it take to separate those out? Well, it's going to take energy because it releases energy to form it. So it's going to take energy to separate apart. But I want them separated. I want them removed from each other. The reason it says removed from each other is that if they're still around each other, they're still attracted to each other. I want to know how much energy it requires to completely remove them so they no longer feel each other. We have completely overcome the attractive force holding these together at all and is completely destroyed. How much energy is that? How does your lattice energy relate to some of the physical properties of ionic compounds or ionic substances? The higher your lattice energy, generally speaking, the higher the melting point and the harder the compound. Because in order to melt something, melting allows those ions to move freely. Okay, so if we've got something, so solid state is the lowest amount of energy we have. It needs the lowest energy to be in solid state. It needs the most energy to be in a gas state. Liquid is in the middle. I've got something in the solid state, and it's locked into a crystalline solid. That's these oppositely charged particles locking itself into the solid structure. I'm melting it. In order to melt it, that means that they are freely moving around each other. These ions are no longer locked into their structure and they can move. That takes energy. And I'm trying to let them move when they're fully charged particles around each other, which means I'm going to take even more energy because I need to destroy some of the attractive force holding that together so they can actually melt. That's a higher melting point. It's also harder compounds. They lead to a harder or, physically hard, harder compound. Important thing to note, again, I know I've said this before, I will say it again, bond breaking, endothermic. No exceptions. It takes energy to break a bond. I've got 2 things together here, okay? I've got 2 random atoms bound together. I want to break these apart. That's going to take energy to break those apart. To send this way and this way takes energy. No matter what, it takes energy to break a bond apart. How much energy? That depends on the bond, but it takes energy to break them apart. Bond breaking is always endothermic. Bond formation, on the other hand, is always exothermic. The only reason a bond is going to form is if it's an energetically favorable reason for it to form. It's not going to form if it's not going to release energy. It may not release a lot, but it will release energy. So lattice energy, the amount of energy it requires to separate 1 mole of a solid crystal into its ions far removed from each other, is a measure of the strength of an ionic bond. How strong is that ionic bond? Well, how much energy does it take to separate it? Coulomb's law, I recommend going to check out this website. The PhET simulation on Coulomb's law is helpful and can help you kind of play with it and see how these things correlate to each other. But the electrostatic force of attraction between charged particles is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. Basically, force times distance is your energy. Force times distance is what force is applied over a certain distance is related to your energy. So your potential energy between your charged particles is directly proportional to the product of the charges, inversely proportional to distance between the charges. Q is each charge, R is the radius of each charge. What does this really mean? This is Coulomb's law. Basically, what it means is this. The closer an electron is to the nucleus, the stronger attraction, the lower the electron's energy. So, Coulomb's law, F equals K times Q1 times Q2 divided by R squared. F is your force of attraction or repulsion between two charged particles. Q1 and Q2 are the magnitudes of the charges, meaning are they +1, +2, +3, etc. R is the distance between the two ions, and K is the proportionality constant. The interaction between an atom's positively charged nucleus and an atom's outermost electrons is what makes each atom behave in unique and often predictable ways. Repulsion between electrons is what makes predicting this behavior more difficult. So if I've got sodium plus and Cl minus, they're attracted to each other. The electrons from that chloride ion are attracted to that sodium ion, but there's other electrons in the way as well. Okay? But we're looking at how much force is this attractive force in between here? What's actually holding these things together? To predict these, you're going to apply Coulomb's law. Generally speaking, the greater the ionic charge, the higher the lattice energy. So that means that +3 is greater than +2 is greater than +1. Generally speaking, the larger the ion, the lower the lattice energy. Remember our trends. This increases size. This increases size on the periodic table. Remember, charge is usually more important than size. So let's look at a couple lattice energies. Sodium chloride. You are not responsible for knowing these lattice energies. I would provide them. I do not have them memorized myself. You will not have them memorized either. But you need to understand looking at the compounds and be able to predict trends without numbers. So for NaCl, the lattice energy is 787 kilojoules per mole. That means it takes 787 kilojoules to separate out ions, 1 mole of ions, from solid state into their ions, far removed from each other for sodium chloride. If I look at Ki, it's 649 kilojoules per mole. This is showing you the effect of size. If you look at the periodic table, you've got sodium, and below it is potassium. Across the table, you've got chlorine, and below it is iodine. So, potassium, bigger. Iodide, bigger. And we see that the lattice energy of Ki is smaller. Why is this happening? You've got these two particles. Na and Cl. And then you've got two others that are bigger. These are not drawn to size. K and I. This energy is holding these together really tightly. It's a really small molecule. It holds really tight. These are just bigger. Remember, this potassium has a positive charge to it. This iodine has an extra negative charge to it. Same thing here, positive and negative. But these molecules are smaller, which means that this negative charge is more attracted to this nucleus. It's smaller, it can reach it easier. This negative charge, although attracted to the nucleus, yes, there's a lot more electrons in the way. They're big molecules. And so the attractive force between them, holding them together, is just not as strong because they're just bigger. If I look at MgCl2, so the difference between, for NaCl to MgCl2, Mg is next to sodium, and then I'm looking at, again, chloride. MgCl2 has a lattice energy of 2,524 kilojoules per mole. The chloride is the exact same thing. The difference here, sodium plus 1, chloride minus 1, magnesium plus 2, chloride minus 1. That plus 2 charge trumps size. That positive charge there, that's a greater ionic charge, leads to a higher lattice energy. And calcium iodide, calcium's underneath, 2,074 kilojoules per mole. So here, I see your size again. Here, I see charge. So, higher charge, higher energy. Larger molecule, lower energy. Let's work a couple examples. I want you to arrange the following ionic compounds in order of increasing lattice energy: NaF, CSI, and CaO. To do this, I want you to think about what do these break up into? Na plus and F minus, CS plus and I minus, Ca2 plus and O2 minus. I immediately see this. This has got a positive 2 minus 2 charge, which means increasing lattice energy, this is going to have the greatest lattice energy. It's going to beat the other two because it's a plus 2 charge. The other two are both plus 1. So I'm going to take this out, and I'm going to look at NaF and CSI. Now I'm looking at the same charge. I have to think about size. This is smaller. This is larger. Smaller will have a larger energy than larger in size. The larger the size, the weaker the energy holding it together. AgCl, CuO, and CrN. Which one has the greatest lattice energy? AgCl, Ag plus Cl minus. CuO is Cu2 plus, O2 minus. CrN is Cr3 plus, N3 minus. Charge is the difference here. Charge trumps size, so CrN. And based upon consideration of lattice energy, which compound is expected to have a higher melting point, NaCl or NaBr? NaCl is Na plus Cl minus, NaBr, Na plus Br minus. Note, the sodium doesn't matter here. I'm comparing these two things, chloride and bromide. Bromide is bigger, therefore lower lattice energy. Lower lattice energy, which means NaCl will have a higher lattice energy, which will lead it to have a higher melting point. It will take more energy to break it apart and let those particles move. So a little bit of review on covalent bonding. A covalent bond is formed when atoms share electrons. 2 electrons equals 1 bond. Covalent bonds typically seen between 2 nonmetal elements, but they don't have to be nonmetal. It does depend on our scale of electronegativity. The 2 measures the strength of a bond length, and bond energy, also known as your bond association energy. The shorter the bond, the stronger the bond. We will learn why in chapter 11. You are not responsible for knowing these numbers, but you are responsible for understanding that your single bonds are longer than double bonds, and double bonds are longer than triple bonds. And once we get to chapter 11, you will understand why. Bond energy for a single carbon-carbon single bond, 347 kilojoules per mole. What that means is it takes 347 kilojoules to break up 1 mole of carbon-carbon single bonds. Carbon-carbon double bond, 611 kilojoules per mole. And carbon-carbon triple bond, 837 kilojoules per mole. Note, this is not a linear relationship. It's not like it takes 347 kilojoules per mole to break up 1 and then double that for 2 and triple that for 3. That's not it. They're not the same type of bonds. We're going to talk about the different types of bonding in chapter 11. Different types of bonds are leading to different energies here. We also, just because it's 154 picometer for a carbon-carbon single bond does not mean that's the same bond length for another single bond. It depends on the atoms themselves. You do need to know this. And I know I've said it before, but you need to know this. So triple bonds, always shorter and stronger than double bonds. Double bonds are always shorter and stronger than single bonds. Bond breaking, always endothermic, no exceptions. Bond formation, always exothermic, no exceptions. A double bond is formed by the sharing of 2 pairs of electrons between 2 atoms. A triple bond is formed by sharing 3 pairs of electrons between 2 atoms. Whereas a single two electrons or 1 pair between 2 atoms. This also gives you your bond order. A single bond is considered a bond order of 1, a double bond, bond order of 2, a triple bond, bond order of 3. So examples, O2 actually forms a double bond. We're going to learn about how we can figure that out in just a bit in this chapter. Different module in this chapter. N2 actually forms a triple bond. CO2 forms 2 carbon-carbon or carbon-oxygen double bonds. And I know we've talked about this before, but this is showing you how do we find this bond length. This is showing for 2 hydrogen atoms. We have 2 hydrogen atoms coming together. As they come together, we eventually reach an energy well or a minimum. That's going to be the bond length of the 2 atoms. If I keep bringing them closer and closer together, the energy skyrockets it again. Because we have that attractive force, we want to form that bond, they want to share electrons so they can lower their overall potential energy. Eventually, though, they get so close that the repulsive force of the electron clouds of the individual atoms takes back over, and when that happens, that increases the energy, and therefore that's not favorable for the bond formation. So we do find that bond during that energy well or minimum.